In the second part of the question, we're going to find a complex number formula for Tn, and then we're going to check the formula by calculating T2. So first I'm going to write out the equation here. And I'm going to let Tn be equal to r to the power of n. So we end up with this if we replace our Tn's with r to the power of n. And then I'm going to divide by r to the power of n minus 1. So basically I'm dividing by the term with the smallest exponent. If you do that, you should end up with r squared is equal to negative 2 r plus 2. Bringing that over to the other side, we get r squared plus 2r plus 4 is equal to 0. Now we're going to use our quadratic equation to solve the roots of this equation here. So we have r is equal to negative b, so negative 2, plus or minus the square root of b squared, minus 4ac over 2a. So we end up with a negative underneath our root, our square root. So it tells us that we're going to have complex roots. Now I'm breaking down the negative 12 into 4 times negative 3, so that will allow me to take 4 out from underneath the square root sign. Now I'm just canceling out all the 2's, so we have negative 1 plus or minus root 3i. So these are our roots here. We have, and they're actually complex conjugates, so if we let alpha be equal to negative 1 plus square root 3i, its complex conjugate will be the other root, which is negative 1 minus square root 3i. And now just as a side note, we can draw these on our complex real plane. So our imaginary real plane, sorry. So the x-axis is the real numbers, and the y-axis are our imaginary numbers. If we want to plot alpha, it has a real value of negative 1 and an imaginary value of root 3. Then it has a modulus of 2, so that's just the length of the line. And it has an argument of 120 degrees. So that's alpha. Now alpha squared is going to have a real value of negative 2 and an imaginary value of negative 2 root 3. And it's going to have a modulus of 4. That's alpha squared. Now alpha cubed is actually going to be just real, and it's going to be 8. Now, to create an equation using our roots, we're going to let Tn be equal to some linear combination, so some combination of our first root to the power of n plus some combination of our second root to the power of n. And we're going to use our two initial conditions to create two equations with two unknowns. So our first initial condition is t0 is equal to 0. So that means 0 is equal to a alpha to the power of 0 plus b alpha bar to the power of 0. So a is equal to a, 0 is equal to a plus b. And then for t1 is equal to 1, we have 1 is equal to a times our first root plus b times our second root. Now if you notice, we have two equations, so we have this equation and this equation here, and two unknowns, a and b. So we can solve these two by just isolating a or b in this equation and subbing into the second equation. And you'll find that a is equal to negative I 2 root 3, and b is equal to I over 2 root 3. So therefore, Tn is equal to negative I 2 root 3 times alpha n, so I'm just subbing in a here, and then I'm going to sub in b, plus I over 2 root 3 our alpha bar to the power of n. Now because these are complex conjugates, this is actually equal to 2 times the real part of the first term here. And this is also equal to the imaginary part of this here. So now to solve for t2, we're going to sub in 2 into the n here, and we're going to take the imaginary part of the result. So we have our alpha, which is -1 minus root 3i, or plus root 3i, squared, and that's squared because our n is equal to 2, and that's all over root 3. If you work that out, it's going to end up to be -2. So that's the imaginary part of this here. And this is what we found previously.